Hey kids, it's Raz. All right, back for part two of air pollution. So today we're going to focus on secondary pollutants, mainly photochemical smog and how that's formed, and also tropospheric ozone. We are going to do quite a bit of whiteboarding in class with this, so really important that we get this in our notes, but don't worry if you're feeling a little overwhelmed because we'll practice with it. So, just to talk a little bit about some of the precursors to photochemical smog. And side note, smog is what you think of if you think of like LA in the summertime. Well, they're hot all the time, but think of like LA and like looking down and kind of seeing like that haze over things. That's smog. Mexico City is famous for it as well, as is a lot, or as are a lot of Chinese cities. So, like, think about those kind of things. That's what we're talking about with photochemical smog. So the first thing is we have to have nitrous dioxides. Those end up getting broken down into free oxygen and nitrous oxide, and it's that free oxygen, that lone O, that can bond with oxygen from the atmosphere to form O3, which is tropospheric ozone. Okay, so that's part of it. VOCs are the other thing. So volatile organic compounds are hydrocarbons. Again, these are coming out of a lot of things that we burn, right? And they bind with that NO to form photochemical oxidants. So anything that's carbon based that volatilizes or evaporates easily is a VOC. They smell bad. So gasoline, formaldehyde, cleaning fluids, like even like the pine smell, like from trees, those are all VOCs. So some of them are naturally occurring. We put a lot more into the environment though. And then lastly, those, there we go. We need that ozone, that tropospheric ozone. And again, it's formed, like I told you, when nitrogen dioxide is broken, or nitrogen dioxide, is broken down by sunlight and bonds with that oxygen. In the troposphere, it is a respiratory irritant and it's damaging to plants. We don't want this down here. It's, again, good up high, bad down low. So we don't want this stuff. So if we're thinking about when this is formed, the conditions that forms this, sunlight is huge because sunlight is going to drive that ozone formation. It is what breaks down the NO2 to get that free oxygen. Without sunlight, it doesn't break down. Warmth is also a condition. So the hotter the atmosphere is, the more chance we have of forming those O3s, more evaporation of VOCs. We have a higher formation of smog. All right, so let's talk about normal ozone formation, how this typically happens. So typically, right, morning commute, we're all driving to school. Well, 7:30, you're already in school, but most normal people are driving to work, right? And we end up with high NO2 levels from car exhaust. There's our NO2. Sunlight, I'm in the way everywhere today. All right, there we go. Sunlight is going to break down that NO2 into NO and free oxygen. And then that free oxygen can bond with oxygen in the atmosphere, and it forms O3. Looks like Mickey Mouse. So we form O3. So typically this is going to peak in the afternoon. Sunlight is most direct. The NO2 emissions for morning traffic have peaked, right? We've got it. It's all out there. So we see this peak in the afternoon. At night, that O3 will actually react with NO to form NO2 again. So it reverts. This isn't something that sticks around forever. So it goes back to being O2 and we'll see ozone levels drop overnight typically. See, it breaks back down. And then we see, yay, there's my little Mickey Mouse. All right, so let's talk about how that contributes to, I'm going to go back because I keep forgetting to pause to let you take notes. All right. So let's go back to photochemical smog formation. We still got our little NO2s being formed in the morning, right? We have our sunlight that is breaking things down. We just went through all this. We have our ozone. Now, VOCs are going to bond. We've got this NO, right, that's now free. VOCs are going to bond with that NO to form what's called photochemical oxidants, okay? If we didn't have NO, we would just have this ozone buildup, and overnight it would go back down. Now, again, ozone is damaging in and of itself, but it would just go back and forth naturally. Because we have those VOCs that can convert that to the photochemical oxidants, that's when we get smog, okay? So you need to have those VOCs there in order for photochemical smog to happen. Okay. Now, what could increase? We kind of already went through this, but if we have more vehicle traffic, you're going to have more NO2. So you're going to have more O3. That will increase it. If we have higher VOC emissions, so if you're out near gas stations or you're near places like plastic factories or petrochemical factories or even laundromats, right? Like even if I love sometimes when I stand outside my house and I'm doing laundry and it smells lovely, but those are VOCs, right? So if we have more of those, that's going to contribute to this. More sunlight. This is typically why we see smog formation in summer afternoons. That's when it's at its worst. Okay. And again, warmer temperatures. Also worth noting that urban areas have more smog because they have all of these factors combined, right? They have more traffic. They have lower albedo, right? So that heat island effect that we talked about, there's warmer temperatures. We have more VOCs because we have more factories and gas stations and things like that. And we have more of an electricity demand. So we have more nitrous oxide emissions from power plants. So it's kind of a perfect storm. Okay. So let's talk about the impacts of this. Then we'll talk about how we reduce it. But impacts, smog is going to reduce sunlight. So it's going to limit photosynthesis. That's going to be damaging to plants. And furthermore, the ozone that's kind of left behind by that damages plants further. In humans, it's a respiratory irritant and an eye irritant. So anybody who already has respiratory issues, those are just going to be compounded. And economically, so we kind of don't really think of this, right? But we see an increase in healthcare costs because of this. We're treating more asthma and bronchitis, COPD, things like that. A lot of times this makes people sick. It makes people not feel good. So we lose productivity at work. I have by people dying too, but mostly it's that we just don't feel good. It's not too often that this will kill people. But we also have decreased agriculture yields. Again, less sunlight, less photosynthesis, we have less ag. So how can we reduce smog? Because obviously this is an impact on a lot of things. First thing is we can reduce the number of vehicles. That's going to reduce nitric dioxide emissions, right? So carpooling, public transport, biking, walking, things like that. A lot of our smart growth and city moves are actually designed to get there to be fewer vehicles. The other side is if we can get fewer fossil fuel burning vehicles on the road, that would be important. We also need to increase our use of renewable energy sources, things that aren't burning fossil fuels when we're making our electricity. I know natural gas is a fossil fuel, but they do release less nitric oxides than coal-fired plants would. So that's another thing. If we can't go straight renewables, is thinking about at least cleaner options. If you feel like doing these, I'm not doing them with you anymore, but this is an interesting little one. We'll actually talk about this in class because you're going to see this. All right, one last thing to mention, and it goes along with smog a little bit, and this is just going to be a quick hit. But we also have a phenomenon called thermal inversions that sometimes happen. So normally, atmosphere is warmest at the Earth's surface, and as we go up, it gets cooler, right? That's common knowledge. Warm air, going back to our wind unit here, right? Warm air is going to rise with convection currents and actually is going to carry a lot of those pollutants up and away from Earth's surface, and it kind of distributes them through the upper atmosphere normally. Now, I'm showing you it. Look, there we go. Now, with a thermal inversion, we have a cooler air mass that gets trapped closer to Earth's surface. And then we end up, so we get this like cold pocket and a slightly warmer above with cold air on top. Sometimes this will happen because we get like a cool air mass and then a warm front that kind of comes in on top of it. Sometimes we get hot urban surfaces that'll cool down overnight. But we're still releasing infrared radiation because it was absorbed during the day. There's a lot of reasons for this to happen. But when that happens, we don't have that convection, right? So that cold air gets trapped there and those pollutants are not going anywhere. And you end up, you can kind of see there, and I'm pointing like you can see in that cooler air layer that there is that stuff, that pollution. If anybody watches The Crown, in some of the early episodes of The Crown, they talk about when this happened in England, because it was a really big deal. And actually a lot of people got really sick and died. It was early enough that we were burning lots of coal-powered plants and we were trapping all of that ick close to the surface. And you can see this picture. I love this picture because you can clearly see that line where that inversion happens and where we're holding all of that smog down there. So again, we're going to see all kinds of flare-ups of respiratory irritation. Obviously, people don't really want to travel in this, so we get less people, coming in tourism-y kind of places, and we get decreased photosynthesis as well because of all that smog. Okay, another little fun thing to look at if you feel like trying to answer it. But we're going to stop there for today, and I'll see you back to talk about indoor air pollutants next. Bye, guys.